Welcome to today's lecture. In our lecture notes, we will today go through section 5.2 about topologies on the real spectrum. So on the real spectrum of a commutative ring, we will introduce two topologies, and we will use Tikhonov's theorem, which we have proved last time, in order to show that they make the real spectrum into a quasi-compact topological space. And the motivation for these topologies is not mentioned in the lecture notes. So I will, at least not at this point, so I will maybe speak about that first. So we are here, topologies on the real spectrum of a commutative ring, and okay. So the motivation is a bit, again, the polynomial ring, for example. So everybody knows the usual topology on R to the n, right? It's generated by the open balls, right? Yes, and here, so we could actually, an open ball is of a form x in Rn, such that the norm of x minus y squared, or x minus y, is less than or equal, is strictly less than epsilon. Okay, so for some center y and some positive radius epsilon, right? So these are the open balls. They generate the topology on R to the n. So that means every open set in R to the n is a union of a finite intersection of such balls. As you know, it's even a union of such balls. You don't even need to take finite intersections. Okay. And you can write this actually as a polynomial inequality, right? You can write that this is x1 minus y1 squared plus etc. plus xn minus yn squared is less than epsilon squared, which you could make into epsilon squared minus, minus this is bigger than 0, right? And the idea is here that we had learned that if you take a polynomial ring over reals in n variables, when its real spectrum is, let's say, closely related to R to the n. So this connection was a bit subtle. So we will learn more about what closely related means. That's actually one of our goals. But what we had already learned is that the Boolean algebra of constructible sets in this real spectrum, and the Boolean algebra of semi-algebraic subsets here, of semi-algebraic subsets of R to the n, are isomorphic, right? That's, for example, one of the things we had already learned. We had already other things, other connections. But we will learn more of these connections, right? And one thing is that here we have a topology. We have the usual topology, Euclidean topology. I was just speaking about it, right? Here we have topology. And here we want the topology, right? And it should somehow be closely related again. These two topologies should be closely related. And, well, we will care about that later, but for a moment, let's just try with some topology. And actually, you know, when we want to make it, of course, more general, when we take actually I want to define a topology on the real spectrum of an arbitrary commutative ring. So that's the idea. And the idea is to do something similar as here. So you take something like, you know, this is here a polynomial inequality, so you could say it's related to a polynomial. So let me turn these xi here into variables. So x1, xn, right? When I could look at this polynomial here, that's a polynomial exactly in this polynomial ring, in the variables xi, right? And when I evaluate it in a little x, so let me call this p. And when I look at all the x in R to the n, such that p of x is bigger than 0, right? Yes, and so the idea is now, so this is a very special polynomial, it's a quadratic polynomial, right? But actually, you know that you could actually, even to define the usual topology on R to the n, you could actually do it also not just by looking at these open balls, but you could actually take any set of this form where p is an arbitrary polynomial, right? Where p is really arbitrary now, right? Because that would define the same topology, because the open balls are a special case of this. All the other such sets are also open in the usual topology, because such a polynomial defines a continuous function on R to the n. And so, so this set will always be open with respect to the Euclidean topology, with respect to the usual topology on R to the n. So you could actually take any polynomial. And that gives us perhaps a way of generalizing this, because we then look here at any element A of our commutative ring, right? And instead of evaluating it at points in R to the n, we evaluate it at the points of a real spectrum. That's just the idea behind this. So we call the topology generated by these sets. So A ranges over all elements of a commutative ring A, and I look at those points in the real spectrum where the real representation of A is positive, right? So you could write this also, if you remember, you could rewrite this as a set of all P in spare A, such that A lies in P but not in minus P, right? You could write it in this way. So the points in the real spectrum are here represented as prime cones P. Okay. So this is the spectral topology on the real spectrum, or sometimes also called Harrison topology. It's named after the American mathematician David Kent Harrison, who died in 1999, and who wrote his thesis with Emil Artin. Although I think he did introduce it only in the case where A is a field, since the real spectrum of a commutative ring was not known at the time when he introduced this topology. So it's probably only on a field where he introduced it. Moreover, we call the topology generated by all constructible subsets of A or equivalently by these sets, where I have, instead of strict inequalities, also equations, right? So topology generated by this is called the constructible topology on the real spectrum of A. So, constructible subsets, maybe let's have a reminder on that. 361. So that was a Boolean combination of such sets, right? So, yes, here the preorder which I take here is just the sums of squares. I don't have a preorder, right? So I take the smallest preorder. So when this becomes really the real spectrum, right? So, so a Boolean combination of such sets, Boolean combinations of such sets, right? And remember that constructible sets can be written in this way, right? So you have finitely many strict inequalities and you have one equation. And you can model this by a finite intersection. So you could write this as something defined by an equation intersected with something defined by a strict inequality, etc. Finite intersection, right? And so that's why I can just take one inequality and one equation in order to generate this topology, which I did here, right? So really the most important topology is the spectral topology. That's more or less the usual topology. This topology is sometimes useful, it's just sometimes useful, right? Unless otherwise indicated, we endow the real spectrum always with a spectral topology. And it is coarser than the constructible topology. That's clear, right? Because it's generating system by which we defined it is a subset of a generating system by which we defined a constructible topology. Let M and N be a topological spaces. A bijection F from M to N is called a homeomorphism if both F and F to a minus 1 are continuous, right? So that means, that F maps the open sets of M exactly to the open sets of N, right? And one calls M and N homeomorphic if there exists a homeomorphism from M to N, right? It's a bit like an isomorphy, you could say, right? But it's a bit on another level because here, it's not an algebraic structure because it's not about relations and operations, it's about this system of subsets. Okay. So let A be a commutative ring when the real spectrum of A is compact with respect to the constructible topology. We endow a two-element set 0, 1 with a discrete topology, right? So let's look at this as two elements. So let's 0 and 1 are, for example, the real numbers 0 and 1. So it's a two-element set, and any subset of it should be open, right? So we begin by this very simple topological space, very boring one. And then, since it's a finite set, it is of course quasi-compact. That's trivial, and also it's compact because it's also Hausdorff. That's because the Singleton sets consisting of just of 0, respectively just of 1, are open, right? So it's compact, and so we know that any product of it is compact. We learned that last time. That was a corollary to Tikhonov's theorem. So any product of it is compact. So I take 0, 1 to be A. So why do I do this? Because when, the elements of this are functions from A to 0, 1, right? I could say Boolean valued functions on A. So these are indicator functions on A. So in some sense, these are the subsets of A, right? The elements of this are the subsets of A. Now you remember the real spectrum consisted, if I view the points as prime cones, consisted of subsets of A, right? So the idea is now start with this compact space and write the real spectrum in some sense as a closed subset of it. And closed subsets of compact topological spaces are compact. That's what we learned last time, right? So closed subsets of compact topological spaces are compact. Okay, so that's the proof strategy. So here it's where we use for the first time Tikhonov theorem. So for every B subset A, we denote by 1b the indicator function, right? And the corresponding characteristic function, I could also say. And now consider the set of all these indicator functions of subsets which are actually prime cones of A. And this is clearly a subset of these Boolean valued functions on A. And we endow it, of course, with a subspace topology of a product topology, right? So with an induced topology. So actually on 0, 1 to the A, we had endowed this with initial topology with respect to the projections, right? PA1, PA2, okay, and so on and so on. There might be many, infinitely many of these. Okay, 0, 1 to the A was endowed with a initial topology with respect to these projections, right? And S is here a subset, is endowed, okay, so here I have a canonical inclusion. So S is endowed with the initial topology with respect to this canonical inclusion here, right? So it's the coarsest the topology on S is the coarsest topology making this map continuous, right? So, but this map is continuous, as you have learned. If you look on the things that we have learned about initial topologies. Yeah, that was this thing here. This map is continuous if all the composition maps are continuous. What are here the composition maps? So this map is continuous if and only if all these compositions here are continuous, right? So since S is equipped now with a coarsest topology that makes this map continuous, that means that S is equipped with a coarsest topology making all these composition maps continuous here, right? Okay. And now, so that means that the topology on S is actually the initial topology with respect to all these composition maps. Okay. So maybe my argument is a bit complicated, but this shows that you can also see it in a more direct way. I guess it's actually very easy. So this shows that the topology on S is generated by the sets of the following form. So 1p of A equals 0, or actually we have a possibility is 1p of a equals 1. By these sets it's generated, right? So okay, so yes, and that you can of course rewrite as a in p. So this can be rewritten as a in p, a not in p, a not in p, and the other thing could be rewritten as a in p. Right? And on the other hand, on the so that's more or less the same as the topology, as the constructible topology on the real spectrum. So we have here clearly a bijection between the real spectrum and S, where I map each element of a real spectrum viewed as a prime cone to its characteristic function. That's clearly, of course, a bijection, right? And what is the topology on the real spectrum, a constructible topology on the real spectrum? Well, let's go back. It's defined, it's generated by such sets here. So let me write it. So it's generated by sets of a form P in the real spectrum, such that, okay, I'm here. So this means A is in P intersected minus P, right? A is in P intersected minus P. And the other thing is this here. This means A is in P but not in minus P. A is in P but not in minus P. Okay, so the thing is that that equivalently I could say that if by taking finite intersections of such sets, I can also play around with A, right? So I can actually write this as, okay, I could write this as this first kind of sets, I could write it as intersection with minus A lies in P. And the second kind of sets I could write as A lies in P intersected with minus I lies not in P, right? Minus I lies not in P. So the constructible topology on the real spectrum is generated by these kind of sets and these kind of sets, right? So yes, but when you see also that it's generated by two, because A ranges over all A in A, so so you see also that it's generated by these four kind of sets. So these four kind of sets, right? Where A ranges over all elements of A. Now, since A ranges over all elements of A, I can equivalently also write here plus A and plus A, right? So I have three. So of these four types, three are the same, right? So I can just keep one of them, and I see that I get exactly the same two types as here, up to this bijection here. So this shows that this is a homeomorphism, right? So I'm sure you can do it. If I did just confuse you, then just find your own argument, which might be even easier, right? Anyway, this is a homeomorphism. That's what I want to say. This is a homeomorphism. And since this product 0, 1 to A, where 0, 1 was equipped with a discrete topology is compact, it suffices by Tikhonov theorem, essentially, right? And because products of Hausdorff spaces are compact, it suffices to show that S is closed in 0, 1 to A, right? Because if S, because when, we had that closed subsets of compact topological spaces are compact, okay? And then when S is compact in the real spectrum of A, also because this is a homeomorphism, right? Clearly homeomorphisms will preserve compactness, that's clear, right? They preserve all structural properties of topological spaces, clearly. And yeah, and so we have to show that S is closed here in this product space. And so in the definition of S, it's most important thing is of course the real spectrum of A. So let's look at the properties of prime cones and let's encode them into properties about their characteristic functions. And let's see if this defines a closed condition, right? So 317 was just a definition of a prime cone of a commutative ring. And so let me just write again the properties that a prime cone P must satisfy. It must be closed under addition. It must be closed under multiplication. We have a condition that P union minus P is the whole of A. A is a commutative ring. Minus 1 is not in P. And we have this condition which resembles a bit to a condition of prime ideals for all AB in A. If a product AB is in P, then A is in P or minus B is in P. So now we should somehow encode this in properties about the characteristic functions. So we could say that, this is all Boolean valued functions on A, let me call them chi, such that, chi of I equals 0 would mean that I lies not in the corresponding prime cone, right? Or B lies not in the corresponding prime cone, or the sum lies also lies in the corresponding prime cone, right? That's just saying that if you have two elements of a prime cones, then their sum must lie in the prime cone, right? Think about it. And I take the intersections over all A, B, and A, right? And the gist will be that this is a closed condition, right? Which this is clearly a closed set here, right? Because it's just saying that it's just talking about the projections, what the projection on A, on B, and so on should satisfy. So it's a finite union of closed conditions, and yes, and therefore it's closed. And when I take possibly infinite intersection, right, of closed sets, which is again closed, right? Remember, finite union of closed sets is closed because where closed sets are complements of the open sets. And for open sets, it was true that finite intersections of open sets were open. And arbitrary intersections of closed sets are closed because arbitrary unions of open sets were open, right? Okay, so that encodes now. So that's why this property is encoded by this one, right? Now the next one is also easy. I mean, it's exactly the same argument, right? And now, yeah, the next thing here, P union minus P is A, can again be written as a closed set, right? And then minus 1 is not in P, can again be written as a closed set. And finally, this condition, right here I just write this. I could say that this is equivalent to AB not in P, or A in P, or minus B in P, right? And this for all AB in A, sorry. So it's that is wrong here, so I have to put here AB in A. This has to be corrected in the lecture notes. Okay, so being thus an intersection of closed sets, S is itself closed, and we are done, right? When S is compact, and consequently the homeomorphic space real spectrum of A with respect to constructible topology is compact. Good. So that was with respect to constructible topology. So I guess such an argument would not have worked for the usual topology, for the spectral topology on the real spectrum of A, right? Nevertheless, we get now also for the spectral topology that it is, well, maybe not compact, but at least quasi-compact, which is the most important thing, right? Okay, so let A be a commutative ring when the real spectrum of A is quasi-compact. Well, why is this? Well, because with spectral, so here I'm talking about the spectral topology, of course, right? If I don't say anything, I mean the spectral topology. Well, the spectral topology is coarser than the constructible topology. That means every set which is open in the spectral topology is also open with respect to the constructible topology. Now, the argument is very simple. So take a cover of real spectrum of A with open sets, right? Then this is also an open cover with respect to the constructible topology, because every open set is also open in the constructible topology, right? But now the constructible topology was quasi-compact, so there is an open subcover. There is a subcover of this cover, right, which still covers everything. Now, okay, since all sets were open with respect to, okay, so that's also an open subcover. I mean, for being a subcover, there is no topology anymore involved, right? It's just meaning that it covers the whole set. Okay, so the argument is quite easy. So if you have quasi-compact topological space, then this is also it will remain quasi-compact if you take topology with less open sets, right? That's just clear by definition of quasi-compact. Okay. So it's actually written here, every open cover of real spectrum of A is in particular an open cover with respect to a finer constructible topology. By 523, it possesses therefore a finite subcover. Okay, so now some reminder on topological spaces. We need a little bit more terminology, which we did not introduce before because we wanted first to prove something, namely Tikhonov's theorem. So let M be a topological space and A a subset of M. The interior, a circ of A in M is the union over all open subsets of A in M. That is the largest open subset of A in M. Because the union over all open subsets of A in M is again open, a union of open sets being open. So it's clear that this is the largest open subset of A in M. Right? And largest means really it contains every other open subset of M and it is open itself. Okay. So the closure A bar of A in M is the intersection over all closed supersets of A in M. So an intersection of closed sets is of course closed. So it is actually the smallest closed superset of A in M. Right? So one shows immediately that a circ is a set of all x in M, such that set of all points in M, such that not only the point is contained in A, but even a whole neighborhood of it is contained in A. Or you could say equivalently, by the definition of neighborhood, you could equivalently say such that there is an open set containing X as an element and being contained in A. Right? And so why is this the same? So, let's look for the two inclusions. So why is the interior of A contained in this? Well, the interior of A is actually open. So if you have a point in the interior of A, then you can take for this neighborhood just the interior of A, right? And the interior of A is certainly contained in A because it's a subset of A. So that's completely clear. And for the other direction, if you have now a point in M such that the neighborhood of this point is contained in A, then you can actually assume or can suppose that this neighborhood is actually open. So we have so when it's actually an open subset of A, and therefore it's contained in the interior of A, and therefore the element X is also is also an element of the interior of A. So that was also easy. Yes, and so for the bar, so for the closure of A, we have the following characterization. That's a set of all X in M, such that for every neighborhood U of X, U intersects A. So the intersection U intersected A is not empty. So maybe let's do this. So first from left to right, let X be in the closure of A. And U a neighborhood of X. We have to show that U intersects A, right? But you know, again, you can assume that, you can suppose that U is open because, I mean, every neighborhood of X contains an open neighborhood of X. And if you can show even for a subset that it intersects A, then yeah, okay. So we can without loss of generality, U is open. And therefore complement of U is closed. And we have to show that we have to show that A is not a subset of a complement of U, right? That means there is an element of A which lies actually in U, right? That's exactly what this set is non-empty here. That's what we have to show. And so if we had that A is contained in the complement of U, because the closure is the smallest closed superset, and complement of U is closed, we would have that closure of A is contained in the complement of U, and therefore X were in the complement of U, which is impossible because U was a neighborhood of X, and therefore X is an element of U. Okay, so that's a contradiction, and yeah, and then we are done. So for the other inclusion, so we prove actually the contraposition. So we suppose that X is in M without the closure of A. We have to show that there exists a neighborhood of X. So we have to show, so we suppose that X is not in the left-hand side here, so we have to show it's also not in the right-hand side here, right? So we have to show there exists a neighborhood of X, U, such that U and A are disjoint. Okay, so you know, A bar is closed, so the complement is open. So that's actually the complement of A bar in M is open. We can set, or U defined exactly by this complement is a neighborhood, actually even an open neighborhood, but that doesn't matter now. It's a neighborhood of X, yeah, because X is an element of it and it is open. It's a neighborhood of X. And now let's see whether it, clearly, U intersected A is empty because that's actually contained in U intersected closure of A, and even that is empty, right? And then we are done, okay? So I'm sure it was not. I'm sure it was not the best way to prove it. The most efficient way. You certainly find better ways of proving it. But that was what I can easily improvise. So therefore, one calls the elements of a circle also the interior points of A. Well, you know, I guess the intuition is that you have here your set A. Okay, and so, and now you have a point here. And instead of saying that a point must be an element, you even say that a whole neighborhood around this point must be in there, right? So maybe like this, right? And yeah, that corresponds to our intuition of interior, perhaps, right? And then the other thing is the elements of A bar are also called adherent points of A. Well, that's, again, our intuition is perhaps that, okay, if you have a point such that each neighborhood of it, no matter how big is it, right? No matter how big it is, each neighborhood of it has a non-empty intersection with a set A, right? Then it should be called an adherent point. That's perhaps our intuition of adherence, right? And well, in particular, elements of A would be adherent points always, right? One says that A is dense in M if the closure of A equals the whole of M, right? So equivalently, you could say if every non-empty open subset of M contains an element of A, right? So why is this equivalent? So you know, this means that every point in the topological space M is actually in the closure of A. So so whenever I have a point X in the topological space M, and you have a neighborhood of it, right? When some point of A must be in there, right? And here you could say, okay, you could say you could restrict yourself to open neighborhoods, of course, again. So that means whenever you have an open neighborhood of some point, then some element of A is in there. But what are open neighborhoods of some point? Well, that's are exactly the non-empty open subsets. Good. Okay, so now let's look again at the real spectrum and at the topology. And we have here a strange phenomenon. So usually in the topologies, you know, probably for example, in R to the n, that's the one everybody really knows, standard topology in R to the n, coming from a usual metric, which itself comes from a usual norm, or you could say from a usual scalar product on R to the n. Singleton sets are closed, right? Singleton sets are really closed. In the real spectrum, that's in general not the case. We will see this now. So actually, we will investigate the closure of a singleton set. So we take one point in the real spectrum, and if I don't say anything, then I mean always the spectral topology, right? So actually, in the constructible topology, that was the somehow unusual topology that we were also considering on the real spectrum. That topology is Hausdorff, right? A constructible topology is Hausdorff. And therefore it's clear that points are closed, right? Because if you have, singleton sets consisting just of one, points are closed. Because if you have a point in the real spectrum, then no other point is contained in a closure, right? If you have another point Q, different from P, then you know in a constructible topology there are disjoint neighborhoods, right? So there is a neighborhood of P and neighborhood of Q, which are disjoint. So in particular, there is a neighborhood of Q, which does not contain P as an element. So, by our characterization of closure, we see that singleton sets are closed in a constructible topology, of course, because it is Hausdorff. But in the spectral topology, this is no longer true, and this might seem a bit strange to you first, but in the end it will make sense. So actually now let's investigate the closure of a singleton set of a point in the real spectrum. So let A be a commutative ring and let P and Q be two points. Then we want to investigate when is it true that Q is in the closure of a singleton set consisting just of P. Well, that's by our characterization of a closure. That's true. That means that every neighborhood of Q intersects a singleton set with P. That means every neighborhood of Q contains P as an element. Okay, so so let me resume what we did so far. So I guess that this equivalence was clear. This one was also clear now, right? So here you can actually, again, it's clear that you can restrict yourself to open neighborhoods of Q, right? I could say an open neighborhood of Q. Okay, so and open sets are unions of finite intersections, right? Okay, so an open set is some union, say over some index set I, of finite intersections, Ji's are finite, of sets of a form P in the real spectrum of A, such that Aij head of P is bigger than 0. Yeah, the Aij's are in A, right? So these are exactly the open sets by definition of a spectral topology. Now, as I said, here you can take open neighborhoods of Q. So you look at such sets which contain Q, right? Since the condition you are looking for is here that P is contained in it, you can actually look just, you don't have to play around with these unions, right? Because if you can show it for all these finite intersections which contain Q, then the same thing is trivially true for all unions of such finite intersections that contain Q, right? If you think about it. Now, in fact, also it's okay not to ignore the intersection, right? Because if you have it for any set like this that contains Q, right? Then you have it, of course, also for any intersection. Doesn't even have to be a finite intersection. When you have it also for any intersection, right? So I could just look at sets of this form, right, where A is just an element of A, right? Just elements of this form that contain Q. So instead of taking here a neighborhood of Q, I take just a set of this form that contains Q. And so this explains that why I say here for all A in A, if A head of Q is bigger than 0, then when P is also an element of the same set, so A head of P is bigger than 0. Right? So I think it should be now clear that this equivalence is also okay. Yes. Now, since A ranges here over all elements of the commutative ring A, I could instead take minus A. If A ranges over A, then minus A ranges also over A. Right? So the next equivalence is also trivial. Oh no, sorry. That was a wrong argument. It's trivial, but it's even more easy. So it's just that instead of minus A head of Q is of course minus A head of Q. So this is in a real closed field. A head of Q is an element in a real closed field, in particular in an ordered field. And instead of saying that this element is bigger than 0, I can say minus this element is smaller than 0. That's the same thing, right? But minus this element is actually minus A head of Q, right? Remember how was A head defined? A head was defined on real spectrum, and it went into a finite a union of real closed. It mapped into a strange union of real closed fields. Anyway, it mapped a point P of real spectrum just to its residue class modulo by support of P in the real closure of a quotient field of A modulo by support of P, together with some order induced by P here, right? Actually, this was this thing here. Doesn't matter now. And when we're real closure. And so, of course, minus A head, of P is minus A residue class, and that's, of course, residue class. It's minus the residue class. And that's, of course, minus A head of P. Right, so that's behind. So it's kind of trivial. This equivalence is also kind of trivial. Now comes the argument I wanted to make before. If A ranges over all elements of A, minus A also ranges over all elements of A. So that explains this thing here. And yes, and then that explains that explains this. And then the other thing is logic, right? Because instead of saying this implies this, I could say the negation of this implies the negation of this. And yes, right? So I get this equivalence, but clearly, A head of P greater than or equals 0 just means A in P, and A head of Q means just A in Q. So this means just P is contained in Q. So this finally shows the last equivalence here. So thus, if there are two prime cones of A that one is properly contained in the other, this is a proper inclusion in my notation, then the real spectrum of A is not a Hausdorff space, right? Because every neighborhood of Q has P as an element. So it's even seems like even worse when not being Hausdorff, right? So in particular, there cannot be disjoint neighborhoods of P and Q. But this case exists, right? For example, it's in the real spectrum of a polynomial ring. I was already speaking about it today, right? So we have always this picture. So we have here PA minus, PA plus, you know what I mean with this picture. And you know, in fact, PA minus is, for example, properly contained in PA. If A is a real number, right? Because whenever you have a polynomial which is in PA minus, what does that mean actually? That means that there exists an epsilon such that P for all x in A minus epsilon, A for all x in this interval, P of x is non-negative, so right, and that that implies, of course, that P of A is non-negative, and that implies that P lies in PA, right? Here the converse is actually also true, and here the converse is also true. But here the converse is not true, right? If P of A is non-negative, is in general not true. So certainly there are polynomials which are non-negative at A, but are not non-negative on the left side, on the left-sided neighborhood of A, right? So that means this is properly contained in PA, and therefore this is contained in the closure of PA minus. So it's not a Hausdorff topology in general. Okay, so now let's see. So suppose A and B are commutative rings and we have a ring homomorphism from A to B. Then we had this map spare phi induced by this ring homomorphism, which went the other way around. So it went from the real spectrum of A to the real spectrum from the real spectrum of B to the real spectrum of A. And it mapped prime con Q to its pre-image under Q, right? This map is continuous with respect to the spectral topologies on both sides, as well as with respect to the constructible topologies on both sides. So that's certainly nice, right? So let's check this. So because for A in A we have, so let's start with the generators of a spectral topology, right? Let's look at their pre-images. So these are very special open subsets of a real spectrum in the spectral topology. And let's start with showing that pre-images of these are open, right? So what is the pre-image under spare phi of this set, right? Okay. Well, these are all Q in spare B, such that I had such that their image under spare phi, right, lies in this set. Okay, so that means a head of spare phi of Q is bigger than 0. Now spare phi of Q is just phi to the minus 1 of Q, right? So I plug that in here. And you know, a head of a prime cone being bigger than 0 means just that A lies in this prime cone, but not in minus the same prime cone. Okay. And, well, you know, taking, okay, minus phi to a minus 1 of q is very easy to see. That's phi to a minus 1 of minus q, right? So maybe let's do this. Minus phi to a minus 1 of q is the set of all, is minus the set of all a in A, such that phi of A lies in q. This is the set of all, this is the set of all minus A, such that a in A and phi of A lies in q. This is a set of all A such that a in A and phi of minus A lies in q. That is the set of all A in A such that minus phi of A lies in q, because phi is a ring homomorphism. That's the set of all A in A such that phi of A lies in minus q, right? Just to be sure that we don't do anything which is not valid. Okay, and that's phi to a minus 1 of minus q, right? Yeah, and you know, taking pre-image is really compatible with all the Boolean operations. So you see actually that this here equals then phi to a minus 1 of q without minus q, sorry. Right. So I see this equality here. And yes, and then that's just rewritten in that way. And that just means that I write it again with a head. So phi, write it with a function that phi of A represents on the real spectrum. Okay, and I see that this is again not only, well, it's open. That's what I wanted to show. Actually, it's again a very special open set. It's again a generator. One of these sets that I specified as generators for the spectral topology on the real spectrum of B. Okay, so now I have shown this for this very special sets, and you know, but when for finite intersections of these, you know, because taking pre-images under maps is really compatible with intersections and so on. So taking a finite intersection of such sets and taking the pre-image of this finite intersection, I get here a finite intersection of such sets. And so it's also true for, so also the pre-image of finite intersections of these sets are again open. And when if I take now unions of such finite intersections, I get here the union again. So taking pre-images is also compatible with unions. And so I see in fact that, I see that pre-images of open sets in the real spectrum of A under spare phi are open sets in the real spectrum of B. Okay. And yes, and now I can do the same thing with, in order to do the same thing for constructible topology, I need to take care of the additional generators which I have in the constructible topology, which corresponds to these things here where I have greater than or equal to, right? But when, that's very easy, so I get here greater than or equal, and here I get this, and here I get just this, and well, I could rewrite it, or again I could copy it, let's say, and then this means just this, and this means just this, right? So that's even a bit easier. And that's again open in a constructible topology, and so on and so on. So with the same argument, it's also continuous with respect to a constructible topology on both sides, right? Yeah, so that's what is written here. Now, last remark for today, let AT now be a preordered ring, right? So a commutative ring together with a fixed preorder T on it. When we had the real spectrum of AT that corresponded to all prime counts of A that contain T as a subset, right? And how can you write this condition? You can just write that P contains a fixed little t in T, means just that T head of P is greater than or equal 0. And that was a closed set, right? That's a closed set in both constructible. Constructible topology, it would even be open, but also closed actually. Right, and in the spectral topology, it's still closed, right? Because it's the complement of it's the complement of the set. So this is the complement in the real spectrum of A of a set of all P in spare A, such that minus T head of P is greater than 0. Which is open, right? So this is closed in a spectral topology, and arbitrary intersections of closed sets are closed, of course, and so this is actually closed in it's an intersection of closed sets, and therefore is again closed in the real spectrum of A, namely with respect to the spectral, but also with respect to a constructible topology. So it's a closed subset of, if you take a spectral topology, it's a closed subset of a quasi-compact space, so it's again quasi-compact. If you take a constructible topology, it's even a closed subset of a compact space, so you have an additional Hausdorff, and so you get it's compact, right? So, yeah, so you see these real spectra of commutative rings, or even as we just saw of preordered rings, are quasi-compact, right? And this seems a bit strange, because I said somehow the idea is that, the real spectrum of a polynomial ring in n variables should be closely related to R2n, right? There should be a close relation between this, and actually we did already some instances of this relation we had already learned about. And I said that the topology here is motivated by the topology here. So what seems strange now, that this is quasi-compact, and this is clearly not the case for R to the n if n is a positive integer, right? Not quasi-compact, except if n is 0. right? So how does this go together? By the way, why is this not quasi-compact? I think that's really a little exercise, right? You can do it really very easily. Okay, so how does that go together? Well, the idea is that actually at this point we want the real spectrum to be fundamentally different from this geometric space, right? We want actually this quasi-compactness. That's one of the big advantages of a real spectrum, right? This quasi-compactness is one of the big advantages, right? And of course we have to pay a price for that, right? The price we have to pay, if you look at the real spectrum of a polynomial ring in just one variable, the price we have to pay, you know, we had this, we had some, so for every real number we had 3 points in the real spectrum, right? And well, one of them corresponds to a real number if you want, right? So we PA, and the other two are some additional points. But the price we have to pay for the compactness is actually the 2 points at infinity and at minus infinity. These make the thing compact, right? Just like, you know, the idea is just like a little bit the interval 0, 1, the usual interval 0, 1 in the real numbers, that's compact, but without 0, 1, it's not compact, right? And because we have these things at infinity here, you could say that is probably the reason why we get compactness. And then of course we have to pay a price, but yeah, that's actually it's we prefer usually to pay this price. Yes. So the points at infinity make this thing quasi-compact, it seems. Okay, thank you for listening. I hope you enjoyed it, and I hope we see us next time when we go to section 5.3 on the real spectrum of polynomial rings, and we actually find a more explicit description of real spectrum via Bröcker's ultrafilter theorem. Thank you very much. Goodbye.